Okay, so from that handout, you drew a curve between those 2 points that was continuous, so you never lifted your pencil. So in number 2, what of the following has to occur if you drew a continuous curve? 5, 4. A root. If you draw a curve between those 2 points, you have to cross the x-axis if it is continuous, if you don't lift your pencil. Some people may have just drawn that. Some people may have drawn something like that. Okay? No matter what, you have to cross the x-axis at least once. Okay? The third one, which of the following heights is the function guaranteed to reach? Pod 6. That's you guys. 2? Why 2? Okay, so y is 2 is in between these 2 points, correct? Is that the only one? Also -1. -1 is a y value in between these 2 coordinates, and so we know it has to reach there at some point. Okay? Let's go to the back side. Okay. You were to draw 3 graphs. If we have discontinuity, we aren't necessarily guaranteed to meet those specifications. So I peeked at Logan's graph. He had this for one of them. Okay, we have a discontinuous graph that doesn't hit the y value of -1. Okay, what's another graph? One with an asymptote. Something like that? Yeah. Good. Okay, so what I wanted you to kind of get from this is if we have 2 coordinates, then the y values that are in between those 2 coordinates, as long as we have a continuous curve, we're going to hit them somewhere in between those 2 points. Okay? So your intermediate value theorem that you filled out, right? Given a function f of x that is blank continuous, should be the word in that first blank, on the interval a to b. Okay. If d is between f of a and f of b, then there exists a c between a and b, where f of c is going to hit b. Do you need me to write that out? Can you write that out? Yeah.
The last space, would that be f of d or just d?
Just d. Okay. Real life examples. Anyone give me one? Logan?
I said the plant was an inch tall last week and is now 2 inches tall, then it had every height in between.
Okay, so if it's an inch tall this week, and then next week it grows to 2 inches, at some point it had to be an inch and a half, right? Josie?
It's when driving, you're trying to get from point A of school to point B of home. If someone needs a ride home, you might consider like whether they live between your continuous route before offering to give you a ride home.
Okay, so if we think about distance, right? If you travel from point A to point C, and there's going to be like a B in between, is that kind of what you're thinking? Okay, okay. We can make it. Anything else? I'd like to play one. That was good. Okay, so in your homework tonight, you're going to have 2 problems. They're like 2 problems on a different page than the rest of your assignment. Okay? if you are given a curve, okay, we know that this function is always continuous, but I'm telling you that the interval is from 0 to 1. Okay? The interval that we're worried about is 0 to 1. Okay? And then it's going to ask you to prove something, like prove that it hits this specific y value. Okay? What do we need to know about this curve in order to use the intermediate value theorem? We need to know what about the endpoints of the interval? We've been talking about height this whole time, right? Intermediate value deals with the height of our function values, right? So what do we need to know about the endpoints of our interval? Their height. F of 1, let's start with 0. F of 0 is negative 1. F of 1 is 2. So a conclusion that we could draw from this there must be a C value where C is between 0 and 1, where f of C equals, what's a y value in between there? F of C has to equal what? There has to be, we don't know what it is right now. I don't really care what it is right now. But there has to be an x value, that's our C, that when we plug it into our function, we get a height of 1. Because on our interval, it stretches from negative 1 to 2. That's the range of that interval. So we have to hit somewhere between. Okay? That is the intermediate value theorem. Questions?
Please release all American Spirit Summit attendees to the Hall of Champions. Please release all American Spirit Summit attendees to the Hall of Champions. Thank you.
Okay. All right. Thank you for going through that with me. Okay. We had so much to talk about yesterday that it's nice to save that piece for today. Today, the rest of the notes, they're not going to be very long. Okay. What I want to talk about now are infinite limits. Just kind of giving you a heads up on schedule. Today we're going to talk about infinite limits. Tuesday we're going to talk about limits at infinity. And then we're going to have a review test. Okay. Not all next week. There will be a quiz next week and then a test the following week. But after today, we only have one more new section. Okay? So, let's talk about infinite limits. Okay? We talked a lot about asymptotes yesterday with our discontinuity discussion. Okay? If we look at limits that are unbounded, I've been telling you that they don't exist, right? Unbounded behavior doesn't exist. And it still doesn't exist, but now we can actually describe how it doesn't exist. Okay? So before, if I asked you these limits, you would put does not exist. If we have that unbounded behavior, I now want you to put either infinity or negative infinity. Does not exist technically would not be incorrect, but I want you to describe it if it is the unbounded behavior. Okay? So the function I have graphed up there is 3 over x minus 2. That is as simplified as that fraction can get. So we know that wherever the denominator is 0, we have a vertical asymptote. Okay? At this vertical asymptote, we have that unbounded behavior as we approach it. Okay? So if we look at the limit as x approaches 2 from the right side, it increases without bound as we get closer to that asymptote. So we're going to call that positive infinity. On the left side, if we look at the limit as x approaches 2 from the left side, it is decreasing without bound. So we call that negative infinity. Graphically, this is what it's going to look like. If I give you a limit analytically, okay, which means you have the equation, you don't have the graph. The only time we are going to have an infinite limit today is when we're at an asymptote. Okay? So if we can identify where we have vertical asymptotes, we can figure out where those infinite limits are. Okay? So, that is the first thing we need to practice. If there is a vertical asymptote, then we know we're going to have some sort of unbounded behavior there. If there's a hole, then we know we can evaluate the limit. So it's important for us to understand the difference in what our equations are doing, so we can either evaluate the limit or describe it as unbounded behavior. Okay? So that's the first thing that we are going to practice. Okay? So I have 3 functions up here, and I want us to think about where we could have vertical asymptotes. Okay, so the first one, 1 over 2 times the quantity x minus 1. Michael, is there a vertical asymptote in that equation? Where? Okay, we have a vertical asymptote at x equals 1. That fraction cannot reduce anymore, and so where the denominator is 0 is the vertical asymptote. Okay. Second one, x minus 2 over x squared minus 4. Logan.
Negative 2.
There's a vertical asymptote? You think so? Okay. Do you agree with Logan? What would be easier to visualize where these are? What should we probably do with the... Logan probably did this in his head, right? What should we maybe write down so we can see what's happening? Okay, we need to factor that denominator so we really know what's happening. So this is what happened in Logan's head, right? What is happening at x equals 2? There's a hole at x equals 2. So if I asked you the limit as x approaches 2, you'd be able to give me a value. If I asked you a left or right hand limit as x approaches negative 2, you'd have to describe it as either infinity or negative infinity. What about secant of x? Does secant of x have any asymptotes? It has 2 holes. Okay. So if I asked you to evaluate the secant of pi over 2, what would you write? Undefined. That is because there is an asymptote there. Okay. if we think of the reciprocal function, right? Technically, we have a fraction here. Wherever our denominator is 0, we have vertical asymptotes. Okay? So the secant graph does have asymptotes at pi over 2 and and every pi interval. At pi over 2 and 3 pi over 2 in one rotation of the unit circle, secant is undefined, and then we can just keep going. Okay? Okay, so now we understand how we identify vertical asymptotes. Let's use that to help us evaluate some limits. Okay. Go ahead and write down your function. We are going to look at the right hand and left hand limits as x approaches 1. Okay, what's happening? If we try to just do direct substitution, we get -1 over 0, right? Okay, so then you might think, okay, can I reduce my fraction at all? We can't. Okay, we can't reduce our fraction at all. So then you need to come to the conclusion, okay, we have a vertical asymptote at x equals 1. So we know that we have unbounded behavior. Is this going to go to positive infinity, or is this going to go to negative infinity? Okay, so this is what I'm going to have you do to figure that out. Okay, this is telling us here that the limit doesn't exist. We know it's at an asymptote, so we know we can describe it as infinity over negative infinity. Okay, so we're approaching 1 from the left side. So let's think of numbers to the left of 1. 0, half. Well, let's think of small numbers, right? If we plug numbers like 0 or 1/2 into our function, what kind of numbers would we get in the denominator? Would we get positive or negative numbers in the denominator? We would get negative, right? If we plug numbers in to the left of 1, this denominator would have negative numbers. So as we approach this 0, we're approaching that 0 with negative numbers, right? So we're getting -1 over -1, and then -1 over -1/2. And then -1 over -1/4. So as we approach this 0, we're approaching so negatively, so we're getting negative over negative. So this is going to approach positive infinity. Do I need to go through that explanation one more time? If we plug numbers in towards the left, like 0, we're getting -1 over -1, and then -1 over -1/2, and then -1 over -4, -1 over -1/8. As we're approaching that 0, we're approaching so in the negative direction, so our numbers are turning positive. Okay, let's think about the asymptote here. From the right side, okay, if we use direct substitution, we get -1 over 0. That's happening because we have a vertical asymptote. So how are we approaching this 0? If we plug numbers in to the right of 1 to our denominator, what kind of numbers will we have? we'll have positive numbers. If we plug in 2, we get negative 1 over 1. If we plug in 1/2, we get negative 1 over positive 1/2. So we're approaching that 0 from the positive side. Negative divided by a positive is negative infinity. Okay. Are the right and left hand limits the same? Are the right and left hand limits the same? So if I asked you for the limit as x approaches 1, you would tell me it does not exist. Yeah.
So if you want, like, if you gave that to us on like a tester quiz, you want that blue to be like our final answer.
Okay. So if I gave you the blue as a question, I would want this red in work to get to here. Does that answer your question?
But like if f of x equals negative 1 or x minus 1,
Mm-hmm.
if you ask that on the quiz, would you want what's in blue to be our answer? It's like good for x.
Yes. Okay. So what we did over here, we talked about left and right hand limits separately. Like probably on the test, you're going to get some right and left hand limits, and you're going to get some regular limits too. So here we just went through what happens on the left, what happens on the right. What does that mean? Okay. Now, let's say here is g of x. Okay. If there was a question like this, where I'm asking you for the limit as x approaches 1, okay? We try to do direct substitution, we have 1 over 0. That's happening because at 1 there is a vertical asymptote, okay? So what you're going to have to do is look at what's happening on the left-hand side of our asymptote and what is happening on the right-hand side of our asymptote. And are they going to be the same? I was getting excited about that square. Oh. Better? Okay. So let's think about the left-hand limit. Okay? Obviously, we're getting 1 over 0, which is because we have an asymptote. We need to figure out, are we approaching from the positive or negative side of 0, so then we can describe which infinity it is. Okay? If we plug values in to the left of 1, like 0, 1/2, what kind of numbers, positive or negative, are we getting in our denominator? Positive. 1 over positive numbers is going to give us a positive number. We're approaching infinity. On the right side, we're getting 1 over 0 again, but which side of 0 we're approaching here? If we plug in numbers to the right of 1, like 2 and 1/2, as we get closer and closer to 1, are we going to get positive or negative numbers as we approach that 0? Positive again, right? So, on the left-hand side of the asymptote, we're unbounded towards infinity. On the right-hand side, the left-hand side, on the right-hand side, we're also unbounded towards infinity. And so, to answer the limit as x approaches 1, we would say infinity, because both right and left have the same unbounded behavior. Any questions about any of that work? There's not a lot of work to show, it's a lot of thinking about what's happening, right? Okay, so if we try to do direct substitution, we get 2 over 0. Okay? Can we simplify this any way to where we don't have 0 in the denominator? We really can't we? Okay. Sine of x is kind of stuck there. All right. Even if we tried to use the sine of x over x rule, if we tried to group x and sine of x together, we're still going to be stuck with 2 divided by x. We're still going to have a 0 in the denominator. Okay? So we're kind of stuck, which means we probably have some unbounded behavior here. Okay? So as we approach 0 from the right side of sine of x, are we doing so positively or negatively? Let's recall what the sine graph looks like. As we approach 0 from the right side, are those positive or negative values? They're positive values. So we are approaching infinity. Okay? Now, I know there's no such thing as a positive or a negative 0, right? We're just kind of using the idea as we're approaching 0, we're doing so with positive numbers. Or as we're approaching 0, we're doing so with negative numbers. That way we can figure out which kind of infinity we're going for. Does that make sense? Okay. It's more of just kind of a side note to us, like there's really not a negative. Okay, a couple properties that you could write down, or you could just look at them in your book. Okay, these are in your book for you. If we have the limit as x approaches c, if the limit toward of f is infinite, but the limit of g is an actual value, when you add them together, okay, just make sure you're not Snapchatting me somewhere. Please don't. If you add 2 limits together where one is infinite, it's going to be an infinite limit. If you multiply 2 limits together where one is infinite, it's going to be an infinite limit. If you divide 2 limits where your denominator is infinite, then that limit is going to go towards 0. Why does that make sense? Okay, as your denominator goes towards infinity, that fraction is getting smaller and smaller and smaller and smaller, so it's going to be 0. All right, one more example. Okay, I have f of x and g of x. Both have some discontinuity. Neither of them are unbounded. So why are we talking about this? I want to look at the limit as x approaches -1 from the left of f of x divided by g of x. Gina, what is the limit as x approaches -1 from the left of f of x? Negative 1? From the left, put negative 1, y value negative 1. We're good. What about the limit as x approaches negative 1 from the left of g of x? Josh, what is that? 0. Okay, so technically this limit doesn't exist, but since that's an undefined fraction, we can describe it as either infinity or negative infinity. Okay, so as we approach 0, or as we approach negative from the left, what kind of values are there as we approach 0? They're negative values. So we have negative values as we approach 0, and we have a negative 1 in our numerator. So when you divide negative numbers, we get a positive number. So this limit we can describe as positive infinity. All right. We have 5 minutes left in class. I want you to open your book, and I want you to do at least, let's see, look at your gold sheet. Before you leave, I want you to at least do number 1 and 2 for page 88 before you leave. They're looking at graphs.
Just so you know, have that schedule.
I know, which is why we only have 4 minutes left. Thank you.
Yeah.